Okay, so let's take a look at several sample problems. So the first one, the resistive one. Okay, so resistance R is 200 ohm, and the sinusoidal alternating EMF device operates at amplitude EM and at frequency. This is a linear frequency, the normal frequency, not the angular frequency. Okay, so you need to multiply 2 pi to be omega d. Okay, what is the potential difference VR across the resistor as a function of time t, and what is the phasor VR of t? Okay, so so actually for resistor it is very trivial. So it's nothing but VR of t is 36.0. Okay, it's the same as this one, and then cosine of 2 pi times fd times 60 times t, okay, which is 36.0 cosine 120 pi t, okay, and then the SI unit is V. Okay, and then so VRT is something like this. This is the VR of t, and then the phasor VR is 36.0 V. Okay, this is the phasor. Okay, this is the phasor. So for resistor, it is very, very trivial. And then it also asks you what are the current IRT and the phasor IR. Okay, so IRT is nothing but VRT over R, so which is 36.0 over 200, and then cosine of 120 pi t. Okay, so this is nothing but 0.18 cosine 120 pi t, and then the SI unit should be A. Okay, IR of t is something like this. And then the phasor IR should be 0.18 A. Okay, this is the phasor. Okay, so very trivial for the resistor. Okay, so the next one, we change the resistor to be a capacitor. Okay, so it also asks you the same thing. What is the VC of t, and then what is phasor VC? Okay, so actually VC is nothing but 36.0 volt. Okay, so nothing special. It is just the same as this EM. Okay, this EM is 36, and then the angle is 0. The phase is angle. The phase is 0. Okay, so it's a real number. VC to be 36.0 volt. And then VC is actually 36.0 cosine 120 pi t. Okay, so nothing special. So it's just the same as this E. So for the next part, what is the current IC in the capacitor and the phasor IC? Okay, so if you don't want to play with the phasor, okay, you can also use IC equals C dVC dt. Okay, so that you will get the same answer. You will also get the same answer. But here we try to use the phasor. Okay, so here IC is actually J omega C VC. J omega C VC. So this is the reciprocal of the impedance of a capacitor. So the phasor is looking like this. So here we have a J, and then omega is 120 pi. Okay, this is omega, and then C is 15 microfarad. 15 times 10 to negative 6. And then VC is 36.0. Okay, so this is the IC. So it turns out to be J times 0.203. Okay, of course you will be familiar to write the complex number like A plus BI, okay? But yeah, I think all the textbook in the electrical engineering like to write it as A plus JB, okay? You always try to put the J in the front. I don't know why, but I get used to it already. So I would like to write it like this. Okay, and also the SI unit is A. So this phasor of the current is a complex number. Okay, so here we can actually write IC of T as 0.203 cosine of 120 pi T. Okay, so the frequency doesn't change. And actually this thing J times something is actually, you can also write it as 0.203 exponential to J pi over 2. Okay, you just try to change it to a polar form, 就是极坐标 polar form of a complex number. Okay, so this is actually pi over 2. So this pi over 2 is this pi over 2. Okay, I think in high school mathematics you know how to change a complex number using the rectangular coordinate into the polar. So this is amplitude, this is the phase. Okay, so this SI unit is also A, something like this. Yeah. Okay, so for the third case, so here we have an inductor, so we have this inductance, and it also asks you the same thing. So similarly, we have VL equals 36.0 volt, and also VL of T equals 36.0 cosine of 120 pi T. Okay, so nothing special, we just repeat it the second time. Okay, so we still have this expression of VL of T and also the phasor VL. So for question B, what are the current IL and the phasor capital IL? Okay, so actually IL is equal to VL over J omega L. Okay, so this is the impedance. This is the impedance of the inductor. Okay, so it is actually 36.0 over J, and then omega is 120 pi, and then times L is 230 times 10 to the negative third power. Okay, so this is the inductance. Okay, so this complex number is negative J 0.415. Negative J 0.415. Okay, so if you try to write it as a polar form, so it becomes 0.415 exponential to J negative pi over 2. Okay, or the phase should be negative pi over 2. So actually the idea is like it is here. So this is negative pi over 2. Okay, just now if if it has a positive imaginary part, it is here, so this is pi over 2. This is pi over 2. Okay, for this one, this is negative pi over 2. Okay, something like this. Yeah, so here, this is actually the phasor IL, or you can use this expression. So IL of t will be 0.415, and then cosine 120 pi t, and then minus pi over 2. For this case, if you still want to use VLT equals LDILT dt, in this case, we know this part. We need to take the integration. So that we can find IL. So it may be more complicated. Yeah. So here, that's the point of using phasor here. Okay, so computing the phasor is just like computing algebraic calculation. Okay, with some complex number. Okay, finally, if you get this complex number in the polar form, okay, so you can change. This one is the amplitude, this is the phase, and then with the same frequency, then it's done. Okay, so next we have a series RLC circuit. Okay, so this is different from the previous damped oscillation. For this damped oscillation, we don't have source. We only have RCL, and then closing this loop, and then we only have initial energy stored in the RLC circuit. But here, we don't consider any initial energy. We have a source. Okay, even though it has initial energy, it will decay. So later on, all the response in this RLC circuit will be dominated by this AC source. Okay, so here we have this source E to be EM times cosine omega dt as before, and actually the current is given by I to be this expression, where I has the amplitude, or I should say this is the absolute value or the amplitude. Okay, it should be something like this. The amplitude of I should be, so this is the absolute value, the absolute value， 绝对值，或者是那个 amplitude， 这个复数的绝对值，就是 a 平方加 b 平方开根号这个。Okay, so this is I. The absolute value of I should be EM over this whole thing, and why if we like that. Okay, so the idea here is like we have this E, we have R, so the impedance of R is R itself, but the impedance for LC are not LC only. Okay, so the impedance for the L should be J omega L, and then this is 1 over J omega C, and these RLC are in series. Okay, so for series impedance, they can add together. Okay, they can be added together. So the total impedance Z is ZR plus ZL plus ZC. Okay, so here we have R. R is a real number, so we just put it here. And L and C are imaginary part. Okay, so we have a common of a J and then omega, or omega L, omega DL, omega DC. Okay, so we have a omega DL, and here J is in the denominator. If we put it in the numerator, if we like to rationalize it, or so it becomes a -1. Okay, -1 over omega DC. So for the imaginary part, it is something like this. So the idea here is like if we take the absolute value of Z, the total impedance, so this becomes the real part square, R square plus the imaginary part square. So omega dl minus 1 over omega dc square, and then take the square root. So the I there is like we have Em all over this absolute value of C. So it becomes that one. Okay, so that's why we have this expression, and also we will have a phase. Okay, so we also have this phase. This phase is not 0 degree plus or minus pi over 2 anymore. It will be angle, something like on the right hand side, on the first quadrant or the fourth quadrant. Okay, as much as R is this R is a positive value. Okay, so it must be on the right side. Okay, but whether this part is positive or negative, it depends on the value of L and C, and also the omega d. Okay, so so if this part is larger, so if omega d L is larger than 1 over omega dc, then this imaginary part will be a positive, and otherwise it will be negative, or maybe it can be a 0. Okay, it may also be a 0. But so this angle is somehow like it can be like between 0 and 90 degree, or 0 to negative 90 degree. But this angle is actually defined by this part of this imaginary part over the real part. Okay, so which is something like if you have a complex number, this is a plus jb. Okay, so this angle phi is this tangent phi will be b over a. Okay, so this is just something simple, analytic geometry or some trigonometry knowledge. Okay, so so we have this tangent of phi to be this imaginary part over the real part. And here it also mentioned that this RLC circuit can resonance， 这个叫做共振，它有一个条件，so it has a condition which is 0L plus 0Z to be 0, which means the imaginary part of this Z is 0. Okay, in such a way, we will maximize this I. Okay, if we try to maximize this absolute value of I. Okay, EM cannot be changed, R cannot be changed, but here we would try to, L and C also cannot change, so the only thing we can change is omega d. So if we can tune omega d such that this thing becomes 0, so this square will become the smallest value, and then the denominator also becomes the smallest value, so we will maximize this absolute value of I. So the idea of resonance is like we try to maximize the amplitude of this current. Okay, so to maximize the current, so we need to make the imaginary part of Z to be 0, or the phi to be 0. So the current in phase will be something like, okay, so if this part is 0, so this is just like square root of R squared, which is R. So it turns out to be absolute value of I to be EM over R, and then V and I are in phase, so that all the phasor to be real value, and then this is the resonance frequency. Okay, so we call this the resonant frequency 1 over square root of LC. So here we still have RLC, but the resonant frequency is 1 over square root of LC. But for the QFIS case, for the damped oscillation, we don't have this AC source. For the RLC circuit, the oscillation frequency is a little bit lower than this 1 over square root of LC. Okay, we need to minus R over 2L and then quantity squared for that one, and then take the square root. So it is slightly smaller than omega D, or actually 1 over square root of omega, 1 over square root of LC. OK， 所以这个是共振跟前面的阻尼震荡是不一样的。阻尼震荡的话是 RLC 没有 AC source， 没有这个源，那它的共振频率会比1除以根号 LC 来的小一点点。那这个是叫做共振频率的话，是说我这个 RLC 是固定的，那我可以动的就是这个 source， 这个 AC source 的频率。那如果这个 AC source 的频率取到1除以开根号 LC 的话，那这个绝对值 I 就是这个电流的振幅就会最大化，因为我们想要把这一个弄成为0，因为这平方嘛，最小值一定是0。那这个是0的话，那算分母的话就会变成是 R 平方，就会最小。那或者是 R 平方的开根号就会变成是 R， 所以这个就会最大化这个绝对值 I， 就是这个共振的频率，就是这个共振的条件了。所以这个是 maximize absolute value of I。 Okay, so actually we can also use the potential method to do the similar things, and actually it will be like VR plus or minus, and then VC plus or minus, VL plus or minus. So in this case, we have EM cosine of omega dt equals VR plus VL plus VR plus VC plus VL. Okay, so this is the KVL. So this is the ground, and then going this way a positive value, and then there will be voltage drop. So equals VR, VC, VL. Okay, so in such a way we have also I in this direction. So VR equals R times I, and then VC is VC itself, and then plus VL is L di dt. And then also we have I equals C dVC dt. So in such a way we can put in this expression to here and also here. So we have a second order constant coefficient ODE. So in such a way we can let's see, or we can keep this I here. So we can try to let me see, we can try to take the derivative on both sides. Okay, we can try to take the derivative on both sides, and then we also try to multiply 1 over LC on both sides. Okay, why we do this? So actually on the left side it becomes EM and then negative sine of omega dt, and then over LC, and then equals R over LC, and then di dt. And then plus this is VC sorry, we do not try to define 1 over LC here. We try to multiply it by C. We try to multiply it by C. So it becomes C here, okay, C here, okay, and here becomes R times C, okay, here also becomes R times C, and then here we have a C dV C dt, C dV C dt, and then plus this becomes LC d2I dt2. Okay, so it becomes, this one will become I, this one will become I. So it turns out to be RC di dt plus I plus LC d2I dt2. So up till now, EMC and then sine of omega dt. And then here we try to divide the whole thing by LC. So it turns out to be negative EM over L sine of omega dt plus R over L di dt, and then plus 1 over LC I, and then plus d2I dt2. Okay, so the leading coefficient becomes 1, or maybe I can just reordering it like di dt, d2I dt2 plus 1 R over L di dt plus 1 over LCI. Okay, so this is the same, actually the same second order ODE, but let me try to write it on the right side. Minus EM over L sine of omega dt. Okay, so here we have this. This source is corresponding to this one. We can consider this to be a G of t. Okay, so actually if we would like to actually solve for this complete solution using the complete solution using the original method, okay, so it will be very, very tedious. I don't think I will try to complete the whole procedure, but yeah, if you have interest, you can try by yourself. Actually, the procedure is like, or you try to make the left hand side to be 0, you try to make d2I dt2 plus R over L di dt plus 1 over LCI to be 0, so it will give you the ICT. Okay, so this is the homogeneous solution, and we also assume that the delta to be smaller than 0, so that it turns out to be something like IC exponential to negative R over 2t, R over 2LT, RT over 2L, and then cosine of omega prime t plus phi. It still have this stuff, but actually when we use this phasor method, if we try to use the phasor method, we actually try to ignore this part. We try to ignore this part. Actually, this part will vanish. ICT will tend to 0 when t is large. When t is large. So finally, just assume that it will just vanish. It will just disappear. So we just ignore it. We don't try to calculate too much. We only care about what is the response due to this input. So later on, you can just plug in IPT is something like A cosine of omega dt plus B sine of omega dt into this into actually d2I into this d2I dt2 plus R over L di dt plus 1 over LCI equals that G of t. That G of t is actually this one. Negative EML times sine of omega dt. Okay, so we just assume the cosine and sine with the same frequency, and then we can try to find this A and B out. And finally, we'll find that this A and B, and then we try to convert it to a sine. Okay, so it turns out to be something like this. So it will be very, very horrible, and that's why we need to introduce the phasor here. So the phasor makes this kind of yeah, terrible things yeah, vanish. We don't try to pay with this pay with this tedious computation. So we just try to use the phasor. So the phasor, we just need to compute some complex number. Okay, after computing some complex numbers, finally, okay, we just convert this complex number into the polar form. This polar form can be correspond to a function of time. Okay, so the amplitude becomes the amplitude of the function, and the phase becomes the phase of the function. So and that's it. So we don't need to play with this differential equation. Of course, in a math class, you need to know how to compute. Or I think you still need to know the procedure of solving a constant coefficient ODE, because it will be useful for your engineering study. But actually, for this specific question, the idea is to use the phasor to skip through this tedious computation. Okay, so here we have a sample problem for the RLC. So for the RLC, so here we have what is the amplitude of the current phasor I? Current phasor I. So first of all, we would like to find Z to be R plus J times omega L minus 1 over omega C. Okay, so this is, or maybe you can write as omega D. Okay, just depends, because we have a FD here. Okay, so R is 200 ohm, and then plus J, and then omega D is 60 hertz, which is 120 pi. So L is 230 times 10 to the negative third power minus 1 over 120 pi, and then C is 15 times 10 to negative 6. Yeah, something like this. Okay, so we just plug in RLC in the expression of Z. Okay, so this is nothing but 200 minus J times 90.13. J times 90.13. Okay, so this is the impedance of this RLC. Okay, so this is the amplitude. So you actually need to find the amplitude. So you need to change it to polar form, or actually I will be EM over Z. EM over Z. So this is actually the phasor of I. The phasor of I. So it will be 36.0. Okay, still 36.0 over this 200 minus J times 90.13. Of course, you can just rationalize it, multiplying 200 plus J 90.13, or you just press the calculator to find it out. Or actually, if you would like to find only the amplitude, so it will be like I will be, the absolute value of I will be 36.0 over square root of 200 square plus 90.13 square. Okay, so it is nothing but 0.164A. Okay. Yeah, so this one is like if you have Z1 times Z2, both are complex number. If you would like to take the absolute value of C1 times C2, it will be nothing but absolute value of Z1 times the absolute value of Z2 individually. Okay, so we can just have the absolute value of 36, which is 36. Absolute value of this one will be 200 square plus 90.13 square. Okay, we don't need to rationalize it and then find the amplitude, although they should be the same thing. Okay. Okay, and then for the question B, what is the phase? So for the phase, tangent phi will be negative 90.13 over 200. Okay, if you still remember, so it is just this part. Okay, this part is the imaginary part of the impedance divided by the real part of the impedance. So including this negative sign. Okay, so it will be negative 90.13 over 200. Okay, so in this case, phi will be negative 24.3 degree. Or you can also write as radian, negative 0.424 radian. Okay, so this is the phase. This is the phase, or the phase difference between the voltage and the current, of the circuit. Okay, yeah. So here we talk about the alternating current circuit. Okay. So here we introduce a idea called instantaneous rate of power dissipation. 就是这个叫做瞬时的power dissipation 的率，就是对 instantaneous rate of power dissipation。因为它们的 V 跟 I 都是sine wave 嘛，所以它每一个时刻的 power 是不一样的。So actually, like P equals I square R for the resistor is like the square of the absolute of phasor I times R times sine square. Okay, so because we have I equals this absolute value of I times sine of omega dt minus phi, something like this. Okay, so if we try to plug in this thing into here, we have this square, and then we also have this square. So actually this is the I, and then this is the I square. This is the I square. So the I square is still a sine, but a shift version. Okay, it shifts to above 0. It shifts to above 0, between 0 and 1. Okay, so actually instantaneous rate is it's easy to calculate, but we cannot really measure this instantaneous rate. Okay, so actually if you use a multimeter to measure some sinusoidal voltage or sinusoidal current, actually it will give you some so-called average value. But if you take the average value of a sine, it turns out to be 0 because half of it is positive, half of it is negative. So how to take the average? The idea is to consider the average power. Or we try to square it and then take the average and then take the square root again. Okay, so it turns out to be a root mean square. So the idea here is like, here we try to take the average of this instantaneous power. It becomes 1/2, or y is 1/2. So it is like we try to integrating this thing for a period from 0 to capital T. Okay, so we try to integrating this part. Okay, this part is just a constant, so we can just ignore it because this part is the only vary with time. So we try to integrating this part for a whole period and then divide by this period. So it's just like taking the average in a period. 那如果是离散的话，就是好像说你算平均值的话，就是把所有值加起来， 除以 n， 有 n 个的话除以 n， 就是比如说全班的平均分哦，全班比如说40个人，那40人的分数加起来除以40，所以这里要除一个 t， 因为你积分了一个0到 t 的时间，所以除以 t， 就是在这个 t 时间里面的平均的 power。Okay, so this one turns out to be 1 minus cosine 2 of this thing. Okay, and then over 2. Okay, so this is the trigonometry identity. So sine squared turns out to be 1 minus cosine 2 times this argument, and then all divided by 2. Okay, so for this part, 1/2 integrating from 0 to t becomes 1/2 of t, and then finally divided by t. So it turns out to be a 1/2. Okay, so we have a 1/2 due to this part. And for this cosine of 2t, and then integrate for a whole period, it turns out to be a 0. So this part turns out to be a 0. This part turns out to be a 0. So we only have a 1/2 where we try to take the average of this sine squared. So the p average will be 1/2 of I squared r. Okay, something like this. Okay, so we have this 1/2 vector. This is not good looking because for the resistor it should be like P equals I squared R. But when we talk about P average, we need to have a factor of 1/2, which is not convenient, or we need to memorize two cases. Okay, when we have a 1/2 factor, so we try to put this 1/2 into this square, so it becomes a I over square root of 2, and then take the absolute value square. And then we try to define this thing as IRMS. Okay, IRMS and VRMS. Okay, so IRMS is the I over square root of 2, and VRMS is V over square root of 2. So when you use a multimeter to measure the sinusoidal, it also gives you the sinusoidal. Okay,